on, right? Yeah, good morning, and it's a great pleasure to be here and have the opportunity to speak. So the topic, I'm not sure how and whether it is related to the topic of the school, quantum matter without quasi-particles. I've been thinking about it last night and still not decided. Let's have a discussion of that, after. I'll be talking about hydrodynamic behavior of electrons and not excluding myself from using quasi-particles. We'll be using quasi-particles. I mean, not today, in the next lecture, but maybe they're not really necessary. So the plan is to, in lecture 1, to talk about general background, hydrodynamic behavior of electrons, and then introduce some experiments and show how hydrodynamics can be probed, and then in the next lecture to discuss more recent developments, the work that we're doing right now, and we'll see how far can we get. So first let me introduce the wonderful people who did this work. 3 amazing students, and Patrick, Lev, and Hao Yu, and senior collaborators from UK and Israel. And now the topic. So when we think about fluids, I mean, usually, this is what we think of: droplets, airfoils, and flows and pressures and stresses and so forth. But on the micro scale, what's going on here is that there are atoms or particles that collide with each other and show, as a result of collisions, they behave chaotically, and that behavior chaotic behavior that they show on microscale leads via some interesting process, cross-graining may be the right word. Via cross-graining, it leads to an orderly behavior on a macroscopic scale. So there are collisions on small scales and chaotic behavior, and then when you go to larger scale, you get collective behavior. And so this is quite interesting in itself, and this is why people are interested. One of the reasons people are interested in fluids and hydrodynamics in general, and it is, of course, quite different from the behavior that we know for one-dimensional system. One-dimensional system, if we have colliding particles, like in this in this familiar example of a Newton cradle, when particles collide, they don't go in the chaotic state. This particle will give its momentum to that particle and become still, and then that one will kick the next one, and then kick the next one, and then the momentum will be transferred fully from one particle to another with no randomization, no chaotization, and so forth. So that's a behavior in one dimension where the dynamics is integrable. In higher dimension, it is not integrable, and so the question is what does it look like in high dimension, right? So I mean, you laugh precisely because we know very well that in high dimension the one-dimensional intuition does not work. So particles in high dimension do not do the same thing as in one dimension. They as they collide, they develop a chaotic behavior, right? And so so in order to understand what's going on. Oh, right. I think this is stuck. How about now? okay, this GIF somehow blocked the pointer. Okay, but maybe I can unplug it. No. Okay, so it looks like the pointer is permanently doomed.
Does the laser work on the pointer?
No, that's my main concern. I mean, I can switch. No, it's not batteries. I mean, I can. But anyway, I mean, I can use my. I can use this as a pointer. Yeah. So if you go to a high dimension back from one dimension, then we know that there is this chaotic behavior on microscales, and then the memory about the microscopic state is erased after one or few collisions, and as a result, there is a more orderly behavior emerging with conserved quantities. And the way this comes about is that the quantities which are conserved in particle collisions, like momentum or energy, become quickly shared among different particles. They are not, after few collisions, they are not a property of a single particle. They become a collective mode. And as a collective mode, they have a very long lifetime, and you can essentially say that after a few collisions, you have to think about coarse-grained system in which the memory about microscopic state is erased, and only the collective modes due to conserved quantities are what's left, right? And then there will be some universal description for those collective modes based on symmetries and conservation laws, and you can introduce density of momentum, density of energy, and consider how it evolves. In time and space because of the dynamics, and all of that is fairly well known. But I mean, the interesting thing here is that because these collective modes, which are arising due to coarse graining and microscopic conservation laws, they're very long-lived. They lead very naturally to striking phenomena. Long-lived also means that there is low dissipation. For example, if you have a uniform flow, momentum being conserved does not dissipate energy. Only gradients dissipate energy, and gradients are weak if the flow is macroscopic. And because of that, a long lifetime, low dissipation, any nonlinearity has enough time to do something, to develop, even if it's weak microscopically, has enough time to develop and do something striking. And so we do have in fluids, we always expect to see some striking nonlinear behaviors at a macroscopic scale. So that's a very quick introduction into fluid mechanics. And maybe let's stop and see if there are any questions. I mean, at this point. There'll be a prize given for the best question.
How much?
Well, it depends on the question. But anyway, so the subject, of course, is not fluid mechanics in general, because that's a whole big, old, glorious subject. We're interested in whether that behavior has anything to do with the flow of electrons in metals, right? And so usually not. Usually behavior of electrons in metals is very different from fluids. Metals electrons collide with disorder and dissipate their momentum by these collisions. However, there are some cases when electron-electron collisions occur at a much shorter time scale than collisions with disorder. And then there is a range of length scales over which hydrodynamic behavior applies. And there are two main classes of materials. There are high mobility electron systems like gallium arsenide in the old days or graphene these days, where just because there is very little disorder and interactions are strong, you are naturally in the regime when electron-electron interactions dominant over disorder. And then there are also systems where disorder isn't weak, like strongly correlated systems, but interactions are very strong. And so there is, in this case, in principle, hydrodynamic behavior can also apply. I mean, here I'm repeating many of the things some of the things that you already heard from Philip Kim and from other speakers, but I think it's good for the introduction to say it again. But I mean, from now on, we will we'll talk about those high mobility systems, graphene in particular, maybe before we jump into it, let me just say that the idea that hydrodynamic behavior can be found in metals, I mean, it's a pretty old notion, and I think it started 50 years ago or something like that, and then developed gradually, and there have been several attempts to look for it experimentally, and then several points in time where the idea was refined theoretically and then again experimentally. But then it really took off recently when graphene appeared, because graphene is a gift material which, among other nice properties, has essentially gigantic mean free path and essentially no disorder and strong interactions, and their hydrodynamic behavior can be fairly easily realized and explored. So a few words about that. Graphene is atomically thin material. Strong interactions arise because Coulomb interactions act through 3D and are not very strongly screened by two-dimensional electrons. And electron-phonon coupling is particularly weak because of peculiarities of graphene. I mean, carbon is a light atom, and carbon-carbon bond is very stiff. Then, in addition, there is no umklapp scattering because the symmetry is such that Fermi surface is small to begin with, and then there are, even though there are two Fermi surfaces at point K and K prime in graphene, like so. Right? If there is a Fermi surface here and another Fermi surface here, there are no umklapp processes scattering between these two Fermi surfaces, because this is a 1/3 of a reciprocal lattice vector, and so two particles cannot do it. Only three particles can, but three-particle umklapp is a very low likely, small likelihood, right? So yeah. And because there are strong collisions and no momentum relaxation, electrons very easily develop fluid-like behavior, and one can identify several regimes where it can be studied. What Philip Kim talked about was the behavior near the Dirac point, where you have an equal number mixture of particles and holes, and it behaves as a relativistic fluid, or particles and antiparticles. And then the other regime is, where it's interesting, is when graphene is doped away from the Dirac point, and you can dope on the electron side, on the hole side, and then you get a small Fermi surface, like in this picture, and then quasi-particles near that Fermi surface, and they will scatter by each other and will be strongly interacting. And that's the regime where most of the experiments on graphene hydrodynamics are being carried out, and also the regime where theory becomes quite interesting. So I'll focus on that, but I think the difference actually in the first lecture at least will not be that big. Well, actually, before that, are there any questions? Ask something just to break.
For a prize.
I don't have my wallet with me, but I can give you this.
That's mine.
All right. Yeah. Well, anyway. Okay. So let's talk maybe a few, say a few things about the conditions under which you see hydrodynamics. I mean, hydrodynamics of fermions, of course, is an old subject since helium-3 was studied. Helium-3 is a benchmark Fermi liquid. It becomes degenerate at temperature below Kelvin, which is the Fermi energy of helium at, under normal conditions, and it is strongly interacting because there is a hardcore repulsion of helium atoms, and all the way down to millikelvin temperature, where it becomes superfluid. It shows, there are 3 orders of magnitude in temperature, which shows a nice Fermi liquid behavior, and it's dominated. I mean, transport is dominated by quasi-particle collisions. There is no disorder, of course, and so there is a fairly wide range of length scales from the collision between particles. We get E, this should be helium, all the way up to system size. And in that regime, one can see viscous behavior, Navier-Stokes equation, and all of that. So with electrons, things are a little different, because on one hand, I mean, Fermi energy is bigger. In graphene, Fermi energy is a few thousand Kelvin. So we are not limited to super low temperatures, and hydrodynamic behavior can be observed at 100 Kelvin, and one doesn't have to cool it down too much. On the other hand, there are phonons, and phonons dissipate momentum, and you want to have, I mean, you want to have, for hydrodynamics description to be valid, you want to have the electron-electron collision mean-free path to be shorter than electron-phonon collision mean-free path. Now that is true for a typical carrier density, that is true below 10 Kelvin. And so when that is true, one should, there is a range of length scales in which hydrodynamic behavior occurs. And the good length scales are longer than electron-electron mean-free path, obviously, and shorter than this number. I mean, the square root of electron-electron and electron-phonon mean-free path. And maybe let me sketch, because I didn't put it on the view graph. Let me sketch where this comes from. So if I write down, very naively, if I write down Navier-Stokes equation, linearize it, and then it becomes just Stokes equation for electron fluid, then I will have, eta the viscosity, Laplacian of velocity, equal to electric field force on the electron fluid. And if I normalize by particle density, then I'll get kinematic viscosity here, which is just momentum diffusion rate. And then, so this equation would be an equation from which I would have to determine conductivity of my electron fluid in the hydrodynamic regime. And you see, it's very interesting because you have to get velocity in order to get current, you have to invert Laplacian. That means that conductivity will become non-local. The relation between current and field will become a highly non-local relation, and more on that later. But if I want to account for electron-phonon interactions, what I can do is just introduce here some damping term. right? And this damping will be due to electron phonon scattering, right? And so if I now take that and invert, you see that that the length scales at which I'm getting, so conductivity will be, if I invert that, conductivity as a function of k will go as 1 over gamma plus mu k square, k square, sorry. And so you see that the length scales at which conductivity goes to, the ohmic limit will be a square root of gamma over nu, and that gives this dependence. Yeah.
What's the relevance of Fermi energy in this game? Can you be at temperatures above the Fermi energy and still in the hydrodynamic regime, as in a classical liquid rather than in a Fermi liquid?
So, I mean, to be above Fermi energy, you want to dope to Dirac point, because, I mean, these are, 10 to the 5 Kelvin, 10 to the 3 Kelvin. I think that's, you don't want that temperature. So you want to dope to Dirac point, and then you are in the regime of quantum critical behavior. There is essentially no Fermi surface, and that's what Andy worked on. So he will tell you everything about it, or if you remember Helium's talk, that's that. I mean, but you don't have to do that. I mean, you have
right. You can be in helium.
Yeah, usually your doped, your carrier density is doped away from Dirac point somewhat, and then because dispersion relation is very steep, I mean, even small doping is enough to raise Fermi energy by a lot, and then you don't have a problem of quantum critical point.
Do you want temperature below or above 10 Kelvin?
Above. Sorry, what did I say? Yeah, no, I think that's, no, you want to be above, because the electron-electron collision rate goes as t squared. Maybe let me write that down. Is there? So that goes as t squared with Fermi energy, and then the electron phonon collision rate goes linearly with t at not too low temperatures, but there is a small prefactor. So when you, because of that small prefactor, when you go to warmer temperatures, this rate wins over that rate, and that happens at about 10 Kelvin. Yeah.
When you go to temperatures which is below 2 kFS, then you will have T4.
Yeah. So then you have more room. You have more room there, but then when you go to temperatures which are that low, your electron-electron collision mean free path becomes microns, and then you have to. I mean, there are no samples that big, or maybe there are, but they have other problems. I mean, optimal sample size is micron, a few micron. And so from that point of view, you want to be, I mean, you want to be here. So it's bigger, not smaller.
You're always assuming EF is non-zero.
Eh?
Yeah, you're assuming EF is non-zero throughout this talk?
Yeah.
Okay.
So it's not zero, and so this is a typical value, not, if I take some carrier density from literature, then that's that. Sorry, forgot to say. So this is all, I mean, all interesting, but if you now ask what's the situation in a typical metal? In a typical metal, even if it's very clean, it's actually pretty hard to reach the hydrodynamic regime because electron-electron collisions go inversely with Fermi energy, and Fermi energy is a volt, and because of that number is very small, and so it's very hard to to be in the regime when this rate is bigger than that rate. You are usually in the opposite regime. mean, there are some exceptions, but let's maybe not worry about that. Okay, so good. So so after that introduction, I mean, let me talk about the following question. I mean, suppose you have a system which is in a hydrodynamic regime. How do you know you are in a hydrodynamic regime? What are the signatures of the viscous behavior? So this is something that people, including us, worked on for quite some time, and there are many different phenomena that can serve as signatures of the viscous regime. And out of this list, I will talk about just one, which I think is interesting because it's kind of striking. So what I'm going to talk about is transport through a constriction. And before we get to Hydra, let me talk about what happens in the ideal Fermi gas. If you have an ideal Fermi gas and you have some point contacts through which electrons can go, or some constriction, or some aperture, or something like that, then there is a well-established theory of how that relates to transport behavior. And it is basically due to these two gentlemen. There is Landauer theory that says that conductance is related to transmitting channels. And what you have to do to estimate conductance is to solve the quantum mechanical problem of particles scattering and back reflecting or passing through that constriction, and then find scattering channels which are transmitting, and then each of them will contribute E square over H times 2 for spin degeneracy, and N will be the total number of transmitting channels. And you can, more accurately, you can define it as a sum of all channels, each channel is contributing transmission coefficient. This can be understood quasi-classically by saying that in order to pass, electron wavelength has to be shorter than the constriction width, or half the wavelength has to be shorter than constriction width. Then there is a mode that can transmit electron, and in this regime, you get transmission, and that's the conductance. And there is a nice semi-classical argument for this formula, and for this formula as well, due to Sharvin, that goes as follows. If you have an electron here, and this electron has to it's scattering, and you're trying to get it through, then depending on its velocity orientation, it will either will or will not get through. And if velocity is oriented the wrong way, it will bounce back, and right way it will pass. And if you count phase space for those electrons that can get through, you get this formula, which is what Sharvin came up with. He also did experiment. He plunged a tip into a metal surface and observed this regime occurring at a low temperature in 3D. But okay, before we move on, let me just say that the summary of the slide, and it's maybe not so intuitive, is that even though everything is written in terms of transmission, the physical picture is that resistance is equivalent to back reflection. Resistance is the measure of back reflection. All these electrons that make it through, they don't dissipate, and the way current is dissipated is due to back reflection. And so if you read Landauer and Sharvin paper from that point of view, then you see that what they're saying is that there is a non-zero resistance for ballistic flow, because ballistic flow, some electrons in ballistic flow can back reflect. So that, I mean, 20 years later, these concepts were introduced. They have been tested in two-dimensional systems. People made controllable constrictions in which the width of the constriction could be tuned by applying voltage on the top gate and the split gate device geometry. And then as you open it up, as you make it wider, you see that conductance indeed follows that proportionality relation with number of conducting channels. And every time one more channel is added, conductance goes up and makes a step. And so that these steps and a straight line, and each step is quantized in e square h times 2. Nice demonstration of that formula. So all of that is well understood. Maybe let's stop and see if there are any questions here. Yeah.
So the gate width, you said it needed to be much larger than the
Sorry.
wavelength of the electron?
It doesn't have to be. So it starts for the quasi-classical limit that I want to be in. It has to be much larger, but you can start. I mean, in this experiment that was done 20 years later, it was proposed. People, of course, reach the limit when you can make the width comparable to the wavelength. And when you make it comparable to the wavelength, you see that you can access even the regime when there is just one conduction channel opening up, and then the next one, and then the next one. Quasi-classical limit corresponds to being in large n limit, which will be my favorite limit. But in these experiments, you can access n equal 1, n equal 2, and so forth. Yeah.
Is there any dependence on the gate geometry?
Oh yeah, there've been a lot of studies of that. But a zero-odd answer is not that much. There are some details that depend, interesting details that depend on gate geometry. One thing in particular is this structure that looks like noise, but actually it turns out that if you optimize gate geometry, it becomes a fairly sharp plateau that arises at a finite temperature. Let's not get into that. Anyway, so now, what do we get when we have a fluid? If I have a fluid and electrons are flowing through as a fluid, I can ask a question, can I beat that ballistic limit? Can I make conductance higher than in a ballistic limit? And it turns out that in this viscous regime, conductance can exceed the Landauer ballistic conductance. And the argument for that is as follows. If electrons flow as a fluid, and there is some collective flow through this constriction, then this bottleneck for transport due to Charvin phase space argument is relieved. And the way it happens is as follows. If each electron bounces off other electrons, then it doesn't matter whether its initial velocity is pointing the wrong way or the right way, because it will be pulled in the constriction by the flow. And even if initially it is such that if this electron was moving ballistically, it would bounce off, now it doesn't, and being pulled in. And one can expect, based on that argument, that there will be higher conductance, a lower resistance in this case. And that's indeed what happens if you do math, and if you write this equation, forget about electron-phonon scattering. If you write this equation for this geometry and solve it, linearized Stokes equation with no slip boundary conditions or zero stress boundary conditions, your favorite boundary conditions. So just solve the classical fluids problem. Then find the flow. You can do it by conformal mapping. Otherwise, what you find is that from that current distribution, calculate resistance and conductance. You find that conductance now is higher than the ballistic conductance, and the ratio is the ratio is of order the width of the constriction divided by the mean free path. So if the mean free path is shorter than the width of the constriction, like in this picture, you will expect a super ballistic flow.
So in this argument that the electron, even not rising in the right direction, will be kind of pulled with the flow towards the opening. Why does it matter that the scattering comes from electron-electron collisions rather than electron-phonon or something else? So the math is certainly only for electron-electron, but in terms of randomization.
So no, I mean, it does matter. I mean, okay, good question. Of course, it does matter because if you play this game with phonons or with anything else that dissipates momentum, then again you're going to see that a new behavior arises when the collision mean free path becomes of order the constriction width. But this new behavior will be resistance growing rather than decreasing as you add scatterers, right? So you will see that as you add scatterers, such that the mean free path is now shorter than constriction width, you get a deviation from this Landauer-Charvin picture, but in a higher resistance direction, not in lower resistance direction. So here the prediction is that conductance will go up and resistance will go down. That's quite unusual because usually we don't get it from any trivial interaction effects. Usually interaction effects is something that makes conductance lower rather than, as in this case, make it higher. So that is interesting. And the other thing that is interesting is that if you take a material such as graphene, and you make constriction, you can do direct comparison of the two regimes in a single device, because if you go to 0 temperature, then the electron-electron collisions are turned off because they are proportional to temperature. And then you are in this regime, and then when you warm it up, you will get into the hydrodynamic behavior, and we'll see this higher conductance. It's a very simple but nevertheless collective phenomenon when electrons help each other to move more easily through the constriction, more easily as compared to what it would be for each of them to do it individually, right? So when this idea was publicized, but before it was published, experiment was done right away, and then by the time it was published, the data was ready. So it's a very simple experiment, as it turns out. You just take a graphene ribbon and carve constrictions in it, and you can make them varying width. And each constriction is equipped with two pairs of voltage probes that allow to measure voltage drop on each constriction individually, and then you run current all the way through from source to drain. And this experiment that was made in done in Manchester showed very clearly that on one hand, at 0 temperature, you get conductance that behaves exactly as expected from Landauer-Charvin formula, and there is a good agreement with no fitting parameters. So the dashed lines, solid lines are data, and then the dashed lines is this formula, and dependence on carrier density is because the Fermi wavelength depends on Fermi energy, and Fermi energy is controlled by carrier density. So one can just use this formula and plot these dashed lines. Do it individually for constrictions of all different widths, and you see it looks pretty good. And then once you establish this behavior at 0 temperature, you can turn on temperature, and you see that as temperature grows, conductance goes up and resistance drops. This drop continues up to temperature of 100 Kelvin, and then beyond 100 Kelvin, presumably phonons take over, and it starts going up. But there is a drop in resistance due to electron-electron collisions, an effect that would be, not so easy to explain by any other mechanism. So I think after that appeared, everyone, including ourselves, got convinced that electron hydrodynamics is real. I mean, they also did various checks to make sure that there is no there's no funny behavior in that sample. Measured conventional for probe transport and all of that.
Question?
Yep.
Is the Stokes equation only valid in the quasi-classical regime?
Good. So the equation I showed is indeed only valid in that quasi-classical regime if when hydrodynamics applies. However, in this regime, I mean, in this experiment, they are because they're going smoothly from ballistic to hydro. They are always in the regime when the mean free path is actually of the order, or maybe, of the order of constriction width, or maybe even a few times longer. So in that plot, in that plot, you see that this drop occurs already when electron-electron mean free path is still larger than constriction width, and then somewhere here it becomes a order of constriction width, and maybe shorter. So it occurs all the way in the crossover. And then in order to understand this behavior in the crossover, I mean, it's not enough to solve fluid mechanics equations. You have to solve the full microscopic problem to understand how you go from ballistic behavior to hydrodynamical behavior. And that's what we did in this paper. There's no reference, but yeah. So there was a paper that appeared before the experimental paper where this problem was solved, and exactly how it was solved. Maybe we can talk in lecture 2 if anyone is interested. But I mean, you will see the machinery. But if you, I mean, it's not so simple to solve the crossover for the crossover regime from ballistic to viscous geometry, ballistic to viscous regime in that complicated geometry. But if you do that, what you get can be pretty accurately described as a conductance which is a sum of the ballistic Landauer-Charvin conductance and the viscous conductance that you derive by solving the fluid mechanics equations. So it's it's a behavior in the crossover, and it seems to describe the experimental data pretty nicely. And so maybe that's the right place to.
When you solve Stokes,
yeah.
Let's say you can impose zero velocity boundary condition, but that means that there is some momentum relaxation on the walls.
Yeah.
But on the other hand, in low temperature limit, you have ballistic conductance, which means that constriction is very smooth, so nothing happens. So how do you reconcile this?
Yeah. So, okay, so when we did the calculation, we played some dirty tricks with boundary conditions, but not beyond anything reasonable. So we didn't use the true boundary conditions like you just said. We assumed, like many people before us, that electrons relax to equilibrium, some kind of equilibrium, when they reach the boundary.
Right, but that means that at low temperature you wouldn't see ballistic
turns out, okay, turns out that that's not so. It's not so because you still leave the possibility for those electrons that make it through the constriction to go through the constriction without any dissipation, and they contribute exactly what they should in Landauer-Charvin framework. Yep. So it's okay. Yeah, I mean, if you do it, and then think about whether that approximation made sense, it turns out that it makes perfect sense. So this is, I mean, well, first of all, is to make the point that yes, indeed, here collective behavior allows electrons to flow more easily than they do it individually. Also, this plot is a potential distribution in the system, induced by the flow. And you see that it's actually an interesting distribution, that potential drops more or less in an uneventful way along the current path, but then on the side there are some regions where potential goes more negative on the negative side and more positive on the positive side. So the electric field, if you think about the electric field in this region, there are regions in space where electric field is pointing against current. And this is because of what we said here. The current, in the hydrodynamic regime, the current field relation is non-local because you have to invert Laplacian. And you can understand, you can understand that field pointing against current from fluid mechanics picture very nicely. And that is reproduced by that calculation in the crossover region. And you can see that when you go to ballistic limit, these spikes go away. So these are signatures of hydrodynamic regime that in the potential distribution, and I think people are now trying to see them by using various scanning probes.
So why are the conductance additive in the crossover?
We don't know. It's a numerical observation. Yeah. We don't even know. No, I think the right answer. We don't know, but numerically it works very well. Yeah. Okay. So a summary for that is that there is this, interesting signature of hydrodynamic behavior, collective flow that is less resistive and less dissipative than ballistic flow, and it proves that in the viscous limit, when fluid flows collectively, it dissipates less than when carriers flow as free particles individually. And it happens, if you think more carefully how it happens, you can understand that it happens due to some kind of division of labor between carriers. In one of those pictures, let me go back. Yeah. What happens here is that because there is this high velocity stream with high velocity in the middle, it pulls electrons through the constriction before it deviates far enough to bounce on the boundary and backscatter. B, in the hydrodynamic flow, fluid is moving slowly near the boundaries because of the boundary condition that Dmitry said, and because of that, carriers near the boundary are nearly equilibrium, and they don't flow and don't dissipate. And so effectively, these slowly moving layers of the fluid shield the fast-moving layer of the stream from interacting with the boundary. And so this provides some kind of self-lubrication, if you will. That's the mechanism for. Yep.
Stupid question then. If the outside is moving slowly, and if you are conserving momentum, wouldn't that scatter the outer layer more quickly so that it wouldn't stay
Yeah, so you're thinking about some kind of Bernoulli effect, right? Yeah, yeah. But I mean, so this is all. Thank you for asking. I mean, I should have said it myself. I mean, this is all linear response. So we are not looking at nonlinearities, no V square contributions yet. I mean, maybe there will be some interesting V square contributions, including the one you mentioned. And also on that same topic, if you look at this picture, you see that in those corner regions where potential becomes more negative or more positive, or electric field points the other way. I mean, if you opposite to flow, if you calculate local pressure, then because of the Bernoulli effect, you get a reduction in pressure. And one can ask, can this reduction become strong enough, for something drastic to happen here? But in linear response, that doesn't happen. But maybe there will be some nonlinear effects that arise. Yeah. Anyways, so I mean, this brings a number of questions. I mean, one can ask, it's a low dissipation flow. Then how low can it be? What are the limits of dissipation, and what are the transport coefficients doing in that regime? Noise and so forth. But I mean, that's all. These are all very interesting questions to think about, and hoping to explore it at some point.